Yay!
Yay! Here's a standard example that you'll find in most texts of finding the force on one particle due to at least a couple of other particles that are scattered around the plane. So in this case, what I've got is a negative charge, and I want to find the force on that negative charge due to the other two positive charges. And then we'll investigate sort of a really cool little circumstance after we find it. Okay, so what do? The problem is there's not just two charges, they're not all in a line, and so there's going to be components. So we're going to have to be a little more careful. The force, here's the way I would suggest doing it. This is the way I do it. The force is just this charge, it'll turn out to be the negative charge, times the electric field at that point, right? Because all that negative charge is doing is it's sampling the local electric field produced by everything else, and then you just multiply the two together. So let's find the electric field at that position, at the position of the negative charge. Well, let's draw it, first of all. What's it going to look like? Well, I'm going to have an electric field coming like this from the plus Q on the top, and then an electric field that looks like that from the plus Q on the bottom. So it looks like if you add these two vectors together, it sure looks like they're the same distance away from the x-axis. So it looks like those y components are going to vanish, and the final electric field is only going to be pointing to the right. Right? So if the electric field is going to be pointing to the right, and the minus charge, it multiplies that electric field, then the force on it should be going to the left, which should kind of make sense because, I mean, if you think about it in the abstract, the positive and negative charges should be attracting each other. So it should end up that the negative charge is going to be moving to the left, right? So we need to separate. This is a good example of separating the idea of forces and fields. Those two positive charges make electric fields that when you add them together are going to be going to the right, but the force on a negative charge is the other way. The force on the negative charge is opposite to the field, and so it's going to be going to the left. Okay, so let's figure out what the electric field is, and then we'll multiply that back in. The electric field at that point, suppose all these divisions are just centimeters, so it's going to be and each one is 5 nanocoulombs, right? So the electric field, remember the way that we did it when you have to do components is kq over r cubed times r vector. K is 9 times 10 to the 9th. 5 times 10 to the minus 9 is the charge. And so just to take a little shortcut, because we've done this is going to be 45 is the kq. The r, let's see, that's a 3, 4, 5 triangle. So this is going to be 5 cubed, 125 times 10 to the minus 6, right? R, in this case, is going to be 5 times 10 to the minus 2 meters, 5 centimeters. So when I cube it, I get that. Okay, so now here's the tricky business. If you remember, this is where a lot of people get screwed up. What is the vector? It's the vector from the charge to the point I'm interested in. So from that, let's do the top one first. From the top Q, what do I have to do to get to the minus Q? I have to go over 4 in the X and down 3 in the Y. So I have to go 0.04 and minus 0.03. That's the top charge. Okay, and now I have to add the electric field from the bottom charge. So that's going to be plus, it's the same business, 45, same distance, 125 times 10 to the minus 6. How do I get from the bottom charge to that point? I still go over 4 in the X, and now I go up 3 in the Y. So this is going to be 0.04, 0.03. Okay, and sure enough, look, I've got the same thing multiplying the y coordinates, except one's plus and one's minus. So these two are just going to cancel. Sure enough, the y components are going to cancel. And all I get in the x is 2 times 45 times 0.04 over 125, blah, 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 blah. I think I've already done it. And what I get is, let's shorten this up, 28 newtons per coulomb. Okay, so that's the electric field. And sure enough, that electric field is pointing in the positive x direction. Okay, so what happens? That minus charge feels a electric field pointing in the positive direction. So the force on it is just going to be Q times E. So it's going to be minus 5 times 10 to the minus 9 times this vector, 28, 8. Whoops, that's too many zeros. And when you multiply those together, what you get is a force that's minus, what did I get when I multiplied it out? 144 micronewtons. That's the force on the thing, right? So the electric field was going to the right, and then I multiply the negative charge, and now I get a force going to the left. That's the way it should be. So the force on this thing is going to the left. Very cool. All right. And that's it. If you had a whole bunch of charges and you want to find the force on some other charge, that's fine. You just have more electric fields to add together. And then at the end, you still just multiply by that Q. So it's the same process. There's sort of a neat little thing we can do, though. Let's do this. Let's suppose that we have this thing and it's right there. So let's say we put this thing, oops. Now suppose this distance is y, and that distance is x. So suppose that the positive charges are y away from the origin, and then the negative charge is x away from the origin. And suppose that y is lots bigger than x. So let's just move this negative charge close to the origin. Well, think about what's going to happen. At first, it's going to be pulled to the left, right? And when it gets right at the origin, what's going to happen is, well, when it's immediately at the origin, then one charge is pulling up, the other charge is pulling down. There's no net force on the charge when it's at the origin. So remember the mistake a lot of people can make. If there's no force, sometimes you're tempted to say, aha, it'll come to a stop. But that's not what happens. If there's no force, that means there's no acceleration. It coasts through, right? It moves at a constant speed through the origin. So this thing will move through the origin until it gets to the other side. And when it gets to the other side, now the force on that charge is pointed to the right. It's going to be the reverse. So if you think, and the farther it goes, the stronger that force is going to be. So this thing is going to just oscillate. It's going to oscillate around the origin. That's kind of neat. Let's figure out the frequency of the oscillations of this thing. All right. So what do we have? We have the force is going to be Q times the electric field. All right. And we said that the electric field was, well, the Q is going to be negative, right? And let's make the charges all the same Q. So I'm going to have a minus. The electric field was 2 times the contribution from each, is what we said, because they're each contributing the same electric field in the same direction. So I've got a 2 times KQ squared over R cubed. Okay, so what's the distance? What is this distance from one to the other? That's going to be my R, my distance. Well, R is just the square root of x squared plus y squared. So R cubed is just going to be x squared plus y squared, the 3/2. And then my R vector is going to be what? Well, it's going to, I'm going to have one with a positive y, one with a negative y, so the y components are going to cancel out. And so the only thing that's going to be left is just the x coordinate. So it's just going to be x, and then the y's are going to cancel. I don't have to worry about them. Okay, so anyway, here's what I'm saying. This is going to be minus 2k q squared x over x squared plus y squared to the 3 halves. But now let's say that our a y is much, much bigger than x. Let's enforce that condition. If that's true, look what we can do. Look in that denominator. If y is a whole bunch bigger than x, then y squared is certainly a whole bunch bigger than x squared. So we can just sort of forget that x squared is sort of negligible at the bottom. So that just becomes y cubed. So this is just minus 2k q squared over y cubed about times x. I'm going to write it sort of suggestively like that. Okay, here's the force. Look at the form of this. And this, I've seen this problem in a couple of books to find the frequency of the oscillations around the origin. And how would you do that? Look at this. This might sort of be reminiscent of what you might have seen in Physics 1. This is a force, and it's what's called a restoring force because it's opposite to the displacement. If you're a positive x away on one side, the force is to the left. If you're a negative x away on the other side, the force is to the right. So it's sort of like a little spring or rubber band. So this thing represents our, if this is like Hooke's law, then that thing that's in front of the x is our spring constant, right? Our sort of elasticity. It's a terrible symbol, isn't it? Because we usually use k for that, but we have this k down here for the electric constant. So I'll try not to get it confused. But anyway, if you have a force that's of the form minus kx, you sort of already know how to deal with that from Physics 1, if you remember. That's why these are sort of challenging problems. But let's go ahead and try it. So what you know is omega, the angular frequency of this thing is just the square root of k over m, k spring over m. I'll try to remember to write that so we don't get it confused. So what is this thing? Well, there's our k right there. So this is going to be the square root of, what do I have? 2k q squared over my cubed. That's our angular frequency. And remember, if you just want regular frequency in hertz, that is omega divided by 2 pi, because there's 2 pi radians, 2 pi cycles, 2 pi radians in a cycle. And so if you do this, our final frequency, let's see if I put the 2 pi in there. How do I put the 2 pi in there? One way I can put the 2 pi in there is just to make it 4 pi squared and put it inside the square root. So if you do that, what you get is 4, let's see, this would be kq squared over, let's see, the 2 divided by 4 is 2 pi squared my cubed. Okay, so anyway, here's the final expression. Here's our frequency. Maybe this makes a neat, there we go, it'll make a neat box. That's our frequency for these little tiny, these little oscillations around the origin. So this thing is going to vibrate, it's going to oscillate with this frequency. If we put these numbers in, I'll keep this try to keep it short. So I've already done it. So if I put the q squareds in, if I put in what the charges actually are, and then the distance y that I've got here in centimeters, and so on, what you get is you get something like 0.6 hertz. So this thing will, the period of this thing is going to be something like almost every 2 seconds, this thing is going to oscillate back and forth. Very cool. So this is how you'd do this kind of an example that it's a challenging problem, but it sort of harkens back to Physics 1. But it's a cool set of circumstances where this thing will just sort of oscillate around the origin. Kind of neat.